Hello, everyone, and thank you for joining us today. My name is Alex Mitchell, and I work in communications at the U.S. Department of Energy's Argonne National Laboratory. I'll be your host for today's National Lab Discovery Series webinar. We're thrilled to have everyone here today to learn about some exciting and important work that has been done by Argonne and partners. The title of today's talk is Plastic Upcycling, Turning Plastic Waste into Valuable Industrial Products. We'll be learning about some novel research and technologies. We'll also learn about partnership opportunities that exist for organizations that are interested in getting involved in this work, which can not only put a dent in the plastic pollution problem, but also offer some financial upside. Our presenter today is Max Delferro. Max is a chemist and group leader of the Catalysis Science Program at Argonne. He is also a senior scientist at the University of Chicago. In addition, he is the deputy director of the Institute for Cooperative Upcycling of Plastics and a principal investigator for the Catalyst Design for Decarbonization Center, both of which are energy frontier research centers funded by the Department of Energy. Before I turn the floor over to Max, I'd like to point out that your microphones will be muted throughout this presentation. If you have questions, please submit them in the chat box and we will address them during the Q&A section at the end of the webinar. Also, if you're having any issues, please put them in the chat and we will do our best to assist you. So without further ado, I'll turn it over to Max. Max, over to you.
Alex, thank you so much, and thank you the OTT office for this opportunity. As Alex was saying, this is a really collaborative project that we developed during the past few years between Argonne and Ames Lab and other universities. I'm going to talk a little bit more why we are here and why we're interested in this kind of research. And then we deep dive a little bit in the technology that we develop at the lab. Why plastics and why we are looking at plastic upcycling and chemical recycled plastics? First of all, we need to think about how plastic fits in the big picture, and in particular, thinking in the future about the circular economy. Plastic is going to be one of these materials. And what we are trying to do, and we really need to have a paradigm shift in how we deal with waste. However, this is our motto: where there is waste, there is an opportunity. And I think everyone from scientists and non-scientists should really think about how can we deal and transform waste in new resources. Throughout the presentation, I'm going to discuss most of the technology and the science that we developed through the support of the Department of Energy initially and still doing from the Office of Basic Energy Science, and some of the more applied research through the ERE, Energy Efficiency and Renewable Energy, and the ARPA-E. This is really a picture of our vision. What we're doing on the bottom is what we are doing right now. We extract oil. We are very good at doing that and transform through refinery crude oil in new products. And in particular, for making polyolefin and plastic, we're talking about olefins, ethylene and propylene. Most of these products we can use, 75 of these products has been used only one time before discarded in the landfill or incinerated to produce energy. In general, there is in the United States, we are roughly below the 10% recyclability rate. In our vision, we would like to take this plastic waste that they use only once or maybe twice, and using catalytic process as an alternative to what we're doing, for example, right now on mechanical recycling and pyrolysis. We like to take this plastic waste that, if you imagine, is a little bit already pre-purified oil, crude oil, and making new products. And in the center, in particular in the ICOP center, we are looking, for example, at lubricants for automotive transportation. We would like to go from polymer to polymer transformation. For example, we already have some very interesting proof of concept that we can take, for example, HDPE, the classic water jug or milk jug, and transform in a bottle with exactly the same thermomechanical properties. In addition, for example, also we want to make fine chemicals, building blocks that can be used to make new molecules. Let's think about a little bit about the numbers and why we are interested from a Department of Energy standpoint, interested in these topics. 6 to 8% of the worldwide petroleum or natural gas has been used every year to produce plastics. Roughly 350, 400 million tons of plastic produced every year, and roughly 75 can be discarded annually. If you think about the municipal waste, I live in Chicago, in our black bin in our alley, 10% of the municipal waste is composed of polyplastics. And in particular, more than half of this total plastic are polyolefin. High-density polyethylene and linear-density polyethylene, polypropylene, and linear low-density polyethylene. I mean, there is a really an interesting opportunity here to really develop new technologies to transform this plastic waste in new products. I was mentioning before about the fate of plastics. Roughly 80% is incinerated has been discarded, and less than 10% has been recycled, and only 30% is still used for applications. I mean, there is a really huge opportunity to divert this plastic waste from landfill or incineration to make new products. Everyone knows, or you should know about the plastic is really a global problem. There are 5 patches that correspond to the water current in the oceans. The biggest one is between the US and Asia, and there is the Great Pacific Garbage Patch is roughly 2 times the size of Texas and 1 foot deep of plastic waste that is floating in the ocean, and correspond roughly to 80,000 tons of plastics that in theory would be nice to recover and transform in new products. Why we're here? Clearly, policies and impact. Before the 2017, most of our waste plastics was sent to China for transformation or for disposal. After the plastic trash ban, now we need in the United States to deal with this huge amount of material. But this, as I mentioned before, this is a really great opportunity for scientific discovery of alternative technology, but also an opportunity to create a new economy based on the waste. Every time I give a public talk about plastic waste, everyone is a little bit misleading on the symbol that is present in each type of plastics. Of course, there is a number, it goes 1 to 7, within a symbol that resembles recyclability. Unfortunately, to date, only number 1, the polyethylene terephthalate, the classic plastic bottle, and the high-density polyethylene, the water jug or the milk jug, has some recyclability content and recyclability effort. 3 to 7 most of the time are ending in the landfill. However, there are some new, very exciting technology, for example, for polypropylene and polystyrene, and for example, for plastics film, like low-density polyethylene and linear low-density polyethylene. In terms of the state of the art of chemical recycling at scale, there are plenty of examples in the literature, in the scientific literature, of example of how to transform plastic waste in new products. The one that are really at the forefront right now is the depolymerization to monomer. In the case, for example, of the plastic bottle, the polyethylene terephthalate, there are different ways to deconstruct PET, methanolic electrolysis, and the idea is to recover the monomers, and the monomers can be repolymerized to the same product, maintaining the thermomechanical properties. And in theory, this is really a very nice material and can be recycled infinite number of times. One of other technology that has been pushed a lot recently is really the pyrolysis of plastic waste to oils. This is unselective technology, unselective reaction, is really eating the polyethylene or the plastic at high temperature without oxygen to produce a distribution of product, solid, liquid, and gases. The gases can be recovered and used, for example, to heat the plant, and the liquid can be blended with existing oil and can be refined to make, again, olefins that can be repolymerized to make, for example, polyethylene. There are some examples also where the plastic waste has been or is incinerated to produce heat and then electric power. Clearly, this is a downside of producing CO2 as a byproduct. This is what we are doing so far. What we need to do and what we are working on is really develop 100 new technologies, maybe 1,000 new technologies to really tackle the problem of plastic waste in the environment. We think that one technology is not sufficient to address the problem, and we really need to work as a team to develop new catalysts, for example, or new processes to tackle different plastic waste. And this is where our initial discovery, that was roughly in 2016, we were interested in using a catalyst made of the perovskites. You can see in these pictures, these are nanocuboid of perovskites, and we deposited through a chemical process some platinum nanoparticles. And because the platinum and the perovskite support as the same crystal structure, this catalyst is very, very robust. And I will show you later some example of these characteristics and why this characteristic is important, particularly for transformation of plastic waste to lubricating oil. Different, for example, from the pyrolysis that I discussed before, this technology uses hydrogen to cleave carbon-carbon bonds. On the other hand, as a characteristic, the product that we are making is very, very narrow. Means we can control the number of chains, of polyolefin chains that we cleave to a single product. And one example, for example, is making tribological oil. In other cases, to making waxes or gases. Depends of what is the demand at that time. Thanks to the Argonne and thanks to the DOE support, we were able to file a series of patents, a portfolio of patents that goes from the synthesis of the catalyst, the use of the catalyst, and the use of the products. We are still growing this patent literature in this area, and we would like to work with you to really take this technology from the lab to the market. Let's deep dive a little bit in the chemistry. I hope that I'm not going too much in details, but the idea is, as I mentioned before, is we want to cleave carbon-carbon bond with hydrogen in presence of a catalyst at high pressure, high temperature. The temperature is roughly the 300 degrees. There is no solvent. It's a solvent-free reaction. And as you can see from this graph, we are able to cleave in a very selective way the long polyolefin chain to a narrow distributed liquid that we call HQL, high quality liquids. What we learned in the past few years that the reaction is independent of the structure and the molecular weight of the product, but what depends is the catalyst per se. And the polydispersity is very, very interesting characteristic of this reaction. In fact, we go from a large polydispersity that initially was present in the polyolefin waste to a very, very narrow distributed distribution. The liquids are very interesting. There is no olefins, so there is no aromatics or pure alkynes. And they have a very particular application, for example, and I will show you later, as a lubricating and tribological oils. The catalysts work with, and this is the first example that we reported, was using polyethylene, particularly high-density polyethylene as an example without branches, and using a standard product Lately, we are moving on the real waste, and in fact, I have an example here of plastic on a plastic bag. The plastic bag was not clean, and it was used as is, and you can see that the product and the characteristic of and the performance of the catalyst are unchanged. The reaction, as I mentioned before, is called hydrogenolysis. Is a structure-sensitive reactions. That means that controlling the particle size, but in this case of platinum, we can control the dimension of the nanoparticles, and the dimension of the nanoparticle provide a different product. For example, we can go from gases for very small nanoparticle to large nanoparticle. We can make, for example, waxes or white oils. And these give us really a tune and fine tune of the product that we want to make based on the catalyst design. As I mentioned before, we choose to use a perovskites, in this case strontium titanate with platinum, because there is a very strong surface nanoparticle interaction called cube-on-cube epitaxy. And because these reactions are conducted at high temperature, high pressure, in a normal support like silica alumina, the platinum nanoparticles tend to deactivate in a very fast way and losing their chemical and catalytic properties. But because we have these characteristics of cube-on-cube epitaxy, the platinum doesn't move on the surface. And in fact, this is an example on the right of the slides where we repeat the reaction. We just add fresh polymers, and you can see the catalytic condition, the catalytic performances doesn't change with the time. That means the catalyst doesn't need to be reactivated every cycle, and they don't need to do, for example, some calcination or filtration to remove impurities. This is an example for 5 times, but we already show that we can do this on hundreds of times without losing the initial catalytic properties. Of course, if we want to really tackle this problem, we need to think about not just gram or milligram scale in our lab, but we really need to provide kilogram scale, both of the catalyst, but also of the process. At Argonne, we are very lucky. There is a facilities called Material Engineering Research Facilities, and their goal is to scale up both product and processes. And in this case, they were able to scale up both of the synthesis of the support, the strontium titanate, from milligram scales to gram scale and kilogram scales, but also the deposition of the metal. And we show, for example, in this beautiful image of the cube-on-cube epitaxy, you can see, if you're interested in the chemistry, this is the platinum nanoparticles, and this is the support, and we have this beautiful cube-on-cube epitaxy that stabilize the platinum also when we start to make kilograms of this material, meaning we are not losing the property from the lab to the pilot plant or to the same or the average amount of catalyst that's needed for some pilot plant experiments. As I mentioned before, the catalyst is really not targeting a single polymer, but we can, for example, produce liquids not just from high-density polyethylene, but also from other type of polymers. Classic example, linear low-density polyethylene. Most of the plastic bag are made of this material. And these are example of real commercial polymer. There was a gift from Dow Chemicals of different molecular weight, linear density polyethylene with different density of branching. And as you can see in the table, under the same reaction condition, the product that we obtain is independent of the molecular weight and the branch density. The same thing is valid, for example, for polypropylene. Different isomers, stereoisomer, IPP, SPP, and APP, under the same reaction condition, the product that we obtain from these 3 different stereoisomers is an atactic short liquid of atactic polypropylene. And this material have very, very interesting, for example, properties for as a lubricating oil that we would like to expand and develop further. While we are targeting this product, the waxes and the base oil is a big market. Globally, is roughly $57 billion. US is roughly $20 billion. In particular, the technology and the catalyst that we are targeting, the product we are targeting is really the waxes, the base oil, and the viscosity modifier. In fact, some of the two of my postdocs that they left the Argonne, they started a startup company called Eternal Upcycling, and they are looking at how we can transform plastic waste through catalysis, for example, to make these products. I talk about tribology. This is when we go from the lab to the market. We start to collaborate with CPChem through a DOE project. And what we look at is the tribological properties of this liquid compared to commercially available liquids or oils. In particular, the group 3 is from distillation of the crude oil. The polyalpha olefins are synthetic oils, and both of them have different properties and for different applications. And what we did, we look at the wear scar and the coefficient of friction. These are the classic two characteristics to define a oil or a base oil. And as you can see from the both plots, the liquid from plastic waste are similar or behave in a very similar way, for example, to the polyalpha olefin 10. And in this plot, I also have a bubble wrap. This is a real bubble wrap from a package that was used as is without any further purification. And as you can see, that the liquids that we obtain from the conversion of bubble wrap behave similar to the polyalpha olefin 10. We start to look at Argonne. We have also a group that is interested in process design, and in particular looking at the techno-economic analysis and life cycle assessment. Of course, these are very sensitive studies. They can change based on the size, the quality of the product, and the quality of the plastics. But what we look at least at the beginning, is a 250 semi-batch metric ton per day of conversion, a mix of plastic, high-density polyethylene, low-density polyethylene, LLDPE, and PP. And also we look at two different case studies when we obtain low liquid yield and high liquid yield, and how this is between them, how there is an impact on the economics and also on the greenhouse gas emission impact. We start from the techno-economic analysis at TA, based on the production of the liquids, based on the high yield and low yield, the cost per kilogram of a liquid can span between $0.6 to $2 per kilogram, $1.8 to $6 per gallon. Very interesting. My colleague at Argonne, they also look at the impact of the catalyst synthesis. And of course, using platinum is one of the major issues here, but also looking at the leasing of the platinum or purchasing the catalyst, but also looking at the final product, that is these polyalpha olefin-like material. In terms of life cycle assessment, hydrogen also plays an important role. In addition to the low yield and high yield of the cost of the production of this liquid, we also look at where the hydrogen was produced, both from a nuclear source, through water hydrolysis, or solar H2 again from water hydrolysis. But in both cases, particularly in the case of high yield, we really have an improvement in the greenhouse gas emission that goes span between the 5 to 7% less compared to the emission associated with the conventional production of group 3 and polyalpha olefin. These are my conclusion, and I'm happy to take and deep dive in more in the technology, but as I mentioned before, we developed this catalytic system to transform particular polyolefins, linear low density, high density, and linear low density polyethylene to new products. This one was an example of lubricating oil, but as I mentioned before, also we're interested in waxes and white oil. The catalyst design plays an important role in the obtaining the desired product, and we can tune and fine tune the design of the catalyst to design to obtain the desired product. There is a lot of fundamental science that we develop and we discover, and we are still trying to understand in depth of why this material and why this catalytic material is interesting and why performing this way. And clearly, from economic point of view, the formation of these narrow distributed liquids that behave like a base oil, similar to the synthetic oil, could have an economic driving for further development. Of course, I didn't do anything by myself. This is really a teamwork of chemists, chemical engineering, mechanical engineering to think about the pilot plant. Scale up played a very, very important role. These are all my collaborators. My collaborators and also help us to discover and develop this catalytic material. And of course, the Department of Energy, both the Office of Science, the EREs, the Energy Efficient Renewable Energy, and the ARPA for the initial funding and for really try to take this technology from the lab to the market. And I think this was my last slide, Alex. I'm happy to have a discussion with the audience.
Yeah, thanks, Max. So before we move on to the Q&A, let's just take a quick moment to discuss how businesses and other organizations can partner with Argonne in this space. So this is an opportunity to understand how strategic partnerships and technology transfer work within the framework of a national lab work and how they can be leveraged for commercial success. So Argonne has a suite of patent-protected technologies that are associated with this work, and the partnerships and opportunities fall within basically two buckets. The first bucket is our organizations can partner with Argonne on collaborative research to further develop certain technologies, pushing them further along the TRL scale. The other big bucket is there are opportunities to license certain technologies. So for anyone interested in having an exploratory discussion with Argonne, we direct you to go to anl.gov/partners. There are a few kind of basic questions that really kind of help the process get started. So you answer a few questions at that web form, and an Argonne Tech Transfer rep will reach out to you if it seems like there's a viable path forward. So with that, and we'll leave that slide up so folks can have that during the Q&A, we'll leave that slide up so folks can have that important information, right in front of them. So with that, it's time for the Q&A, and we've gotten a lot of questions in already. Thank you for the robust questions and interest. Please continue to submit your questions as we proceed. We'll get to as many as we can today, but please know that for any we don't get to today, Argonne will follow up on every question via email in the coming days. So let's start with a question from Hyai Kyung. Max, they're wondering if this work is done with waste plastic. Are there any concerns with impurities coming with plastic waste?
Yeah, so absolutely. We show that we can do both with clean plastic and also post-consumer plastics. We have example where we use, for example, color plastics with presence of additive and fillers, and the catalyst performance are very, very similar of virgin plastics. These are really targeting mixed polyolefins. As I showed before, high density polyethylene, linear low density polyethylene, linear density polyethylene, and polypropylene. And we can treat mix of these plastics.
Great, thanks, Max. And just to make sure everybody's fully clear, so that website is www.anl.gov/partners. So if you just go to anl.gov partners, right, you're going to get a site unavailable. So I put the direct link right in the chat there for anybody who wants to start filling out a form immediately. So our next question comes from Thomas. Thomas is wondering, he says, for the catalytic cleavage of polyethylene, does this only work on linear HDPE chains or also linear low density LLDPE?
It works for both. HDPE, LDPE, LLDPE, and PP.
Great. Next question is from Daniel. He says, how does it work with mixed plastic waste?
Yeah, it's a great question. So far, we really, as I mentioned before, really focus on the mixed polyolefins. And for example, if I start to mix HDPE with linear low density polyethylene, LDPP, we obtain a mixture of product with the same molecular weight. Very narrow polydispersity, but same molecular weight. That can be, again, blended in as a tribological oil.
Great. Next question is from Padmini. Does the plastic need to be processed into a certain shape or form for this catalyst to work? And what is the cost of the plastic pre-processing?
I can answer the first question. I don't know about the cost of the pre-processing, but we can follow up with our TA group at Argonne. We were really targeting plastic films, and we use films and shred films of polyethylene. The shape of the plastic doesn't impact the overall outcome of the catalysis. But for the second one, it's not my strength, the TA, but we will follow up with the TA group.
Great. Next question comes from Bella. If you could please share your perspective on biodegradable bottles. So your perspective on biodegradable bottles.
Yeah, meaning, as I mentioned in my presentation, one technology is not sufficient to tackle the plastic accumulation problem. Polyolefins in general has a great mechanical properties. They change our life in better. And I think we are going to use polyolefin for a long time. However, there are new materials, like as you mentioned, these biodegradable polymers that could have also an impact on packaging, for example. The big problem right now with the current technology that the thermomechanical property of biodegradable plastics are not the same as the polyolefins. And that is really a problem. But I know there are a lot of research and further development on improve the thermomechanical properties of this material to try to be at least as the same of polyolefins.
Great. Daniel is wondering, is this lab scale only, or has a sizable process been built?
The one at Argonne, yes. They do scale up, material scale up. They go from catalytic material, battery material, but also they are looking at process.
Great. Utkarsh is wondering, would you please provide any insights on techno-economic analysis and life cycle assessment analysis of this process?
Utkar, I'm going to follow up with our TA and LCA group to touch base with you and to have a further discussion for more details about that. The only thing that I know for sure is for the life cycle assessment, we use the grid model. That is one of the DOE model to determine the greenhouse gas emission. And the group at Argonne implemented the grid model with plastic waste, in addition to cars. And
great, thanks, Max. Next question is from Saad. how are researchers optimizing the conditions for hydrogenolysis to selectively break down plastic polymers into valuable monomers without degrading their properties?
Yeah, I mean, this take a lot of years. We started this one in 2016, and we're still trying to optimize the condition. I'm very lucky at the lab at Argonne. We have all the tools that are needed for optimization. For example, we have an high throughput laboratory that allow us to do parallel reactions and really speed up the discovery and optimization of new processes and known processes. And if you're interested in high throughput experimentation, I'm very happy to talk offline about these important tools. And in fact, we are looking also the next step, that is really the autonomous discoveries of combining high throughput with machine learning, the AI, and robotic system to discover new polymers or new deconstruction pathways.
Okay. Next question is from Thomas. Is the PE dissolved in the hexane solvent, so a solution phase reactor?
No, the reaction, particularly for this particular reaction, is solvent-free. We are roughly 300 degrees, and the polymer is in the melt form. Clearly, it's a viscous liquid, but there is no solvent involved in this process. And my colleague at Ames Lab, that are part of our EFRC ICOOP, also develop a reactive separation that allow us to obtain through a distillation specific olefins, for example, or specific products, the reactive separation.
Great. Next from Padmini. When there is exponential demand for chemicals and virgin plastics themselves from plastic waste creating circularity, what economic case supports the need for motor oil?
Can you repeat? Sorry, Alex. I missed
Yeah,
you.
no worries. When there is exponential demand for chemicals and virgin plastics themselves from plastic waste creating circularity, what economic case supports the need for motor oil?
This is a great question. I think the market is going to dictate which product do we want to make. In our first example, we were looking at tribological oil for multiple reasons. My wife, she's a tribologist, and it was an easy conversation to have at home, but also at the lab, and now at Texas A&M, Ali Erdemir is a worldwide tribologist, was very interested in these chemicals for some specific applications.
Okay. Next question is from Athanasios. How is the catalyst and the plastic brought in tight contact for the reaction to proceed? It seems that it requires a very fine distribution of the plastic and the catalyst. Also, is a continuous process possible? It seems that the time required forces a batch process. If you'd like me to repeat, I can.
Yeah, let's start from the last question. The initial discovery was a pure batch product. Now we are in a semi-batch, and we can transform plastic waste to liquids as low as few hours, really helping to try to transfer this technology from the lab to the market. The new technology is not based on platinum STO. We have new materials and new catalysts that are more active, that allows the efficient transformation of plastic to liquids. Regarding the contact between the catalyst and the plastics, because we are in a melt, the polymer is melted and the reactor is shaked, or there is a overhead steering, the mass transfer limitations are minimized, even if they are still present due to the high viscosity of the melt plastics.
Great. Next question is from Daniel. Is it a fluidized bed reactor?
Not yet. That is the goal. That is the wish. It's a semi-batch. It's a trickle bed reactor.
Got it. Next question is from Bill. DOE closed FOA applications recently related to plastics. Does Argonne anticipate additional funding rounds by the DOE to enable licensees of such technology to deploy these technologies into commercialization?
Yes, the answer is yes. We are always open for collaboration and funding. We submitted in collaboration with Eternal Upcycling, the startup company. We submitted a proposal and we are waiting to hear from DOE. Hopefully good news.
Great. Ignacio is wondering where you get the water. Can you use geothermal?
So again, where the water
it says the question says, where do you get the water? Can geothermal be used?
Yeah, absolutely. I'm in Chicago. We have the Lake Michigan to get the water. Most of our water came from the Lake Michigan, but of course, energy, the hydrogen production, and the hydrogen will have a big impact. At the beginning of this story, at the beginning of this project, almost 10 years ago, we were thinking that the hydrogen was a problem, but today, with a big investment on the hydrogen economy, hydrogen is not the main concern. The main concern is, for example, is use of platinum as a catalyst.
Got it. Paul from GE Vernova says, thank you for the comments about post-consumer waste. How robust is the process to halogen-containing impurities? In parentheses, it says fluorinated, chlorinated polymers, flame retardants, etc.
Yeah, we didn't look at PVC or Teflon contaminant yet. This is something that down the road, we would like to really test to be sure that the catalyst can survive under this condition. We know that there are some brominated compounds as anti retardant flames, and we didn't see any strong deactivation. However, we need to do a deep dive on these additives and other polymers that are not polyolefins.
Got it. I think you may have just answered this question, but we'll ask anyways just to be sure. Brenda says, can your process handle PVC?
No. I mean, we don't know yet. I don't think so, but you never know.
Got it. Daniel's asking, how do you heat the process?
In the lab, it's power reactors, and there is a mantle that allow us to uniform heat the reactor.
Bear with me one sec. Question from Rajarshi. This is a three-parter, so we'll take it one at a time. Part number one, what is the maximum percentage non-plastic, parentheses, glass, wood, etc., and non-PE/PP plastic like PVC, EVOH, PUR, etc., this process can accept? So what is the maximum percentage of non-plastic this process can accept? I'm sorry, non-plastic and non-PE, PP plastic.
Yeah, we didn't look at the non-PE and PP plastic yet, as I mentioned before, but this is something that we would like to do in the future, maybe in collaboration with some of you. Regarding the non-plastic material, we look at, for example, at composites, where you have aluminum film, PP film, and polyethylene film. And at least based on preliminary results, we didn't observe any issue with the presence of aluminum. But we didn't look at, for example, like glass or wood.
Got it. Okay, part two of the question. Have you done catalyst deactivation studies? Can you regenerate this catalyst? They're saying they guess not, but they're wondering.
Yeah, this is the beauty of the science that we discover on the catalyst, this cube-on-cube epitaxy, that the catalyst, at least only utilizing polyolefins, doesn't need to be reactivated after each cycle, but we can just add fresh post-consumer polyolefins and can be converted to the desired product.
Got it. Okay, part 3 of that question. You mentioned that you have developed better catalysts now. What types of catalysts are those?
We are looking at bimetallic, and diluting the platinum is one of the patent pending, and we can have a conversation offline about that.
Great. Ozge is wondering, did you have a chance to investigate the effect of hydrogen pressure in your hydrogenolysis experiments?
Yes, we look at temperature, pressure, time. I was reading just the comment. I will post these are all public information. There is a paper on macromolecules published a couple of years ago, where we look at all the different conditions, parameters, and different microstructure of the polymer. Linear density, block copolymer, for example, the ExxonMobil Vistamax was also studied in that case. We look at different structures in addition to catalytic parameters.
Okay, Anthony is wondering, are there any initiatives looking at repurposing or recycling some of those other plastics that, as of now, have low recycle value?
Yeah, absolutely. Meaning this is, as I mentioned, and I'm repeating myself, one technology is not enough to tackle the plastic problem. Clearly, if you can go mechanical recycling is one of them, and repurposing some of the plastics. Unfortunately, for some of these plastics, during the mechanical recycling, they are losing some of their mechanical properties, and that is a problem. But that doesn't mean that we should not do that. There are initiatives on that.
Okay, Ron says, "Excellent work, Max. Have there been any efforts to use this catalyst technology in an existing commercial pyrolysis unit?"
We would love to do that. We need you, Ron.
Sounds like maybe a familiar face there. Shri says, "Interesting stuff. New polymers. Thumbs up." Mike, do other byproducts exist from your process, such as hydrogen or SAF?
Yes. We use the hydrogen to produce to cleave the carbon-carbon bond. I had, for the SAF particular, another startup company that came out from our center, this time from Ames Lab. They are looking in SAF from plastic waste and biodiesel and diesel products. Regarding the hydrogen, I had a very interesting conversation a couple of weeks ago with a company in Houston that they have a proprietary transformation to take polyolefin to graphite that can be used, for example, as an anode for batteries and hydrogen.
Great. Daniel is wondering, does the process produce any carbon black, char, or ash?
No, none. That is because there is hydrogen that prevents the formation of any coke.
Got it. Okay, not a question for you, Max, but just a message for the group at large. Ryan chimed in and said, if you're interested in learning more about scale-up and commercialization efforts, please reach out to info@eternalupcycling.com. Okay, question from Ignacio. Sargassum is a polluting algae that invades beaches. Could this sargassum be catalyzed the same as plastics?
Maybe. I don't want to say yes or no. These are biomass materials. There is a lot of carbon-oxygen bond, a little bit different structure. I know, for example, that platinum can cleave ester or ether bonds, and maybe that is possible, but I cannot be sure until we try.
Got it. Looks like just a few more questions here. Daniel says, what is the hexane solvent used for?
Yeah, the hexane solvent in the diagram flow was used to remove the latest the polymer remained, or the liquids remain physiabsorbed on the platinum STO catalyst, and they can be recycled within the process.
Okay. Anthony says, thank you for answering my question. This was an excellent presentation. I look forward to receiving the slide deck. Paul says, do aromatics and cyclics survive?
The product that we are making is aromatic and cyclic free. And that is, again, due to the presence of hydrogen that catalyze the hydrogenation of any aromatics. We never try, honestly, any polystyrene, but maybe this is something that we want to add to our deck of experiments.
Great. Elia says, I think I was skipped over before, but what is the TRL on this? So I think wanting an actual number here it may vary by technology, but
yeah, I will let Sun Jun answer this question. Probably we're in the 4, 5, 3, between 3 and 5, 3 and 6.
Yes, I agree with Max, between 3 and 5. It's demonstrated in lab scale, and we scale up to kilogram scale.
Great, thank you, Sujun. Okay, the questions keep rolling in here. So Pranjali asks, have you tried this reaction in a hydrogen-free environment in the presence of hydrogen donor solvent?
Yes, we try, and the product we are making alkyl aromatics. And there is a group or multiple PIs in our center that are really looking at trying to make selective alkyl aromatics that can be used, for example, as a detergents from plastic waste.
Got it. We are at the bottom of the list now in the chat. If there's, I believe we've gotten all the questions, but if there's anybody who we skipped, now would be a good opportunity to maybe just alert us here at the very bottom of the chat, either by, just maybe copying and pasting your question again here at the bottom. But I think we've covered them all.
And I was reading, happy to share the slides, and I will add the link and the DOI number for each of the publications.
Great, yeah, we'll take a real close look at the chat and make sure that there's follow-up. Sean and the folks at the Office of Technology Transitions who are, giving us this platform, I know that they're really good about sending out the slides as well as the recording to everybody who registered. I would say if you did not register and you somehow made it here anyways, now would be a good time to put your email address in the chat so that we make sure you receive the follow-up materials. Lots of thanks rolling in. So yeah, thanks again to everybody who attended and contributed to the conversation. I also would like to, on behalf of Argonne, thank DOE's Office of Technology Transitions for giving us this platform. Sean and everybody over there do great work, and we really appreciate their continued support. So just for a last time, if you are interested in exploring a possible partnership with Argonne, visit www.anl.gov/partners. So with that, thanks again, everyone. I believe there's going to be a short outro video here, but thanks again for joining us.